Good evening, everybody. I'm glad that you're here. I want to thank the Kansas City section for doing such a great job in organizing this event. When I first learned that I was going to receive this award, my first thought was, what am I going to talk about? I've been retired for 18 years. I've been out of the loop for quite a while. But then I realized that I had some unpublished data from my stint at USDA, my home there for 44 years. So tonight I want to talk a little bit about thermodynamic modeling of triglycerides and the possible connection between modeling and nutrition labeling. Next slide. This is a depiction of the equality triangle of various edible fats and oils. There are three legs to this triangle. We have oxidative stability as one leg, functionality, and nutrition as the third leg. Now, with frying fats that are heated to rather high temperatures, we get into the formation of polymers, free fatty acids, polar materials, and volatile oxidation products. Now over here is nutrition, and recently, I would say in the last 2 decades, nutrition has been the driving force in the edible oil arena. That's because of trans fatty acids that are produced by catalytic hydrogenation, saturated fatty acids, and thank you. Even conjugated linoleic acid has been a factor. Okay, is that better? I hope. Historically, catalytic hydrogenation has addressed oxidative stability and functionality, but with the formation of trans fatty acids, that's become quite a problem. Fats and oils have been the whipping boy of the food industry for many, many years. There's been at least 20 diseases and afflictions attributed to fats and oils. Among them are coronary heart disease, some cancers, obesity, diabetes, liver and kidney disease. So since nutrition labeling became effective in 2006, chemists have had to redesign some edible fats and oils particularly for functionality and nutrition. Next slide. Here I've shown the comparison of oxidative stability with the iodine value of various oils. The iodine value is just a measure of double bonds within a particular triglyceride. And you can see there's a pretty high correlation between oxidative stability and the iodine value. Up here is coconut oil, which is very stable. Down here are fish oils that are very unstable. Here I've shown what nutritionists and dietitians have called unhealthy oils. The fluid cube clear frying shortenings, they're high in trans and saturates. Butter, lard, and tallow, they're high in saturated acids, and they also contain cholesterol. Here we have coconut oil. It's very highly saturated. It's a great popping oil. Then we have palm and palm kernel oil. They're very high in saturated acids, but they're very versatile because they can be fractionated into various levels of unsaturation. And then stick margarines that are used in baking, they're rather high in trans fats. Next one. Here I've shown some data on the rates of coronary heart disease and mortality by year. Start up here at 1950 up to about 2020. And you can see that the number of CHD deaths per 100,000 has dropped considerably over these many, many years. That can be attributed to a number of factors, better diagnostics, consumer awareness of dietary fats, the use of statin drugs to control cholesterol. Here I've shown a kind of a timeline of edible oil usage over the many, many years. Colonial times up till about 1900, butter, lard, and tallow were produced primarily on the farm. And by 1900, cottonseed oil became the dominant edible oil in the market. From 45 to 50, the soybean industry develops hydrogenation and fractionation and all kinds of food formulation technologies. In the 50s, tallow and lard began to lose their market shares. So the meat packers, Armour, Swift, Procter & Gamble, they turned to rearranged lards or treatment of the fat with sodium methoxide to re-scramble the positions of the fatty acids on the glycerol backbone. By the 70s, the palm oil industry started to develop in Malaysia and Indonesia, and they started to be incorporated into food oils. From 85 to 2003, these trans and saturated fats became the focal point of industry's development of new technologies. And that includes trait modified oils. Our group at the Northern Lab got in on the ground floor of bringing low linolenic acid soybean oil to commercialization. Companies developed enzymatic modification, modified hydrogenation, and fractionation of tropical oils. In 1990, Congress passed the Nutrition Education Labeling Act, and it required the labeling of various fat properties on a label. Calories, total calories, calories from fat, saturated fat per serving, and so on. And within about 4 years, about 1,900 foods were reformulated to zero trans. And there was a paper published in 2012 that further developments showed that the trans fatty acid content of oils and foods could be reduced to as low as 0.2 of a gram of fatty acid. So whether these nutrition labeling regulations have had an effect on longevity and a reduction in heart attacks, that remains to be seen. But it was a very expensive undertaking. The FDA estimated that reformulation of a food group would be well over $100 million. But they said that that would save 3,000 lives per year and several billion in medical costs. Next slide. Okay, here's some approaches to fat blending. Up until about 2000, trial and error was used. Chemists got out in the lab and they started blending hydrogenated stocks with liquid oils, and that served pretty well. And these compositions are well noted in the scientific literature. For a while, linear programming was very useful for processing a number of different oils. It was claimed to be cost effective. You could plug in the cost data for various oils and it would be cost effective. Now, neural networks have been published, but usage is very limited. I could only find two publications in the literature. Both of them agreed pretty well with calculated values. Next slide. Now this slide shows the formulation of margarines with hydrogenated soybean oil. Up here is the solid fat content of the base stock, and these are the various dilutions by weight. So a 25-75 blend will result in a soft tongue margarine, and about a 50-50 blend will make a stick margarine. Next slide. This shows formulation of shortenings with hydrogenated soybean oil with added hydrogenated, completely hardened soybean or cottonseed flakes. And it works pretty well. You can make practically any shortening with this type of blending. However, with nutrition education labeling, this is rapidly becoming obsolete. Next slide. Here's a picture of what a triglyceride looks like. You have the glycerol backbone here, and fatty acids are esterified on various positions. The most common fatty acids are lauric, C12, saturated, palmitic, stearic, oleic, linoleic, and then elitic, or the trans isomer. This just summarizes some more properties of triglycerides. I've already covered the fatty acids. The structures conform to a 1-3 random, 2 random distribution. Under this, saturates are found in the outer 1-3 positions. The rest are distributed randomly across all 3 positions. And any excess of linoleic is found in the 2 positions. These materials melt anywhere from -13 to 72. Molecular weights run anywhere from 807 to 891. Tags exhibit polymorphism. That is, they can exhibit more than one melting point. And each of these forms, alpha is the least stable, beta prime is the next stable, and beta is the highest melter. Now each of these exhibits distinct crystal packing structures. They may be like a tuning fork, or a chair, or a tilted chair. Beta prime is desirable for margin shortenings because they impart smooth, shiny textures to the product. Now the beta tending tags are useful in liquid creamy shortenings. These are just hard stocks suspended in liquid oil. Next slide. Okay, here's old thermodynamics of tags 101. Melting point, that's the temperature at which a solid fat becomes a liquid. It may be expressed in Fahrenheit, centigrade, Kelvin, or reciprocal Kelvin. Now here's the enthalpy of fusion, or the heat of fusion, and that's the amount of energy required to convert a solid into a liquid. And it's expressed usually as kilocalories per mole, calories per gram, or joules per gram. Now entropy is a measure of randomness in melting, and it's just the amount of energy that's not available for work in a particular system. Specific heat, that's the energy required to change 1 gram of fat 1 degree C. Now tags obey the first law, and Gibbs free energy applies, and I'll talk about that a little later. Next slide. So here are the goals of tag modeling. If we take interesterified, blended tropical oils, the compositions are not well established. So by using thermodynamic models, we can predict melting point, the solid fat content over a range of temperatures, the crystallization temperature, and the composition of various fatty acids. So that's the goal. Now, here I've shown the functional structural properties of triglycerides. It's convenient to divide tags into four distinct groups according to their melting points. And these are all found in common vegetable oils like soybean, corn, cottonseed, canola, and peanut. Now these furnish nutrition. They contain high amounts of linoleic acid, which is an essential fatty acid that must be consumed because the body can't synthesize it. And as such, these are liquids at refrigerator temperatures, and they're easily pumped, handled, and stored. Now, group 2 tags melt from 6 to 25, and they're going to remain liquid even at ambient temperatures. Now, your group 3, they melt near or at body temperature, and they provide structure beyond ambient temperatures. Group 4, these are very high melting triglycerides. They're not found in natural fats and oils, and they're made by complete hydrogenation of cottonseed or soybean oil. Next slide. This slide addresses lubricity, which when applied to fats and oils can mean a lot of different things. Could be for the separation of gluten in doughs, mouthfeel and tenderness of baked goods, the formation of an oily film and how quickly a fat melts in the mouth. Now, at body temperatures, the fat should melt quickly to give a pleasant cooling effect because high melters tend to give an undesirable, pasty, waxy sensation. Cake batters, solid fat functions to incorporate air into the mixing stage, which ultimately defines the volume of the cake. High shortenings require plasticity at low to ambient temperatures because they're loosely bound in the dough, and it requires solids for texture in this rapidly melting sensation in the mouth. Okay, get into some of the published thermodynamic models. The first one is by Westdorf, and it's the classic model that others have used to build upon. Others have taken DSC data and applied it to saturated tags. Zeeberg uses what he calls the group contribution method, and it's applicable only to saturated tags. Timms published a very interesting paper where he developed equations from the literature to calculate the heats of fusion of various triglycerides according to their what he called his effective carbon number. Now this one is relatively new, and it's developed from the literature, and at one time it was on the website of the American Oil Chemists Society, but it's disappeared. But it's a very handy, user-friendly type model. Then there's been several studies where Murphy's model has been revisited with relation to enthalpy and entropy. And just recently, a very intensive, comprehensive review of all the models appeared. Next slide. I'm going to elaborate a little bit more on the public models. I've already talked about some of these, but you can see that there are quite a few models out there. And one of the goals of our work was to compare our data with these various models. Next slide. Here it shows just the calculations of thermodynamic data from melting points at tags. This is an equation that was developed by a gentleman in Holland. HF equals the natural log of 10 times the gas constant times the slope of the various melting curves. Now, entropy is heat of fusion divided by temperature in degrees Kelvin gives free energy as HF minus entropy times temperature. Next slide. A little bit about our analytical methodology. We used the American Oil Chemists Society official methods, primarily the Mettler dropping point. DSC is useful, but it's very labor intensive. It has to be done very carefully, but we'll see that it's suitable for thermodynamic studies. Okay. Yeah, this is the equation that I referred to. Here's how the data turns out. We, by our method, tristerin is 51 calories per gram. Literature values are from 15 determinations is 52. Next slide. This slide shows we plotted the melting points of various fat blends against temperature. And you can see that we get pretty nice linear correlations between the two. And this is indicative of ideal solutions. Most tags obey ideal solution behavior totally or in part. We had a few that did not obey ideal solution theory at low concentrations, but as they were increased, they became ideal. Next slide. I took some of Hanowic's data and compared it to ours, and you can see that we our data agrees pretty well with what he found, with an average deviation of about 2 grams. Next slide. One of the things I looked at was the variability of melting points of pure tags and fats and oils from the literature. And I'm not going to go through all of this, but generally speaking, methods should agree about no more than a half a degree centigrade. We took a number of tags and ran them in duplicates, and they varied anywhere from 2 to 5/10 of a degree. Next slide. Here's the reproducibility of DSC heat diffusion. Here we have 15 values for tristerin, ranging from 48 to 55, with an average of 52. 13 values for tripalmitin, average 52. SOS, six values from the literature range from 36 to 46. So there's variation between various investigators. Here's a little bit about the method we developed for determining thermodynamic properties. It's a pretty simple procedure. You determine the melting point of the pure tag, make dilutions, redetermine the melting points, plot log concentration versus reciprocal degrees in Kelvin, and then calculate the HF using a modified Clapeyron equation. So, next slide. Here I've tabulated some of the data from our experiments versus models. The heat diffusion, you can see that pretty much our melting point method agrees pretty well with all the other published models. Here I've compared melting point data with DSC and effective carbon number, and again we show pretty good agreement between our experimental data and the models. With the exception of POP, which is the agreement, that's not very good. Surprisingly enough, there's very little thermodynamic data on the properties of industrial fats and oils. So we looked at a number of various fats, beef tallow, coconut oil, lard, palm oil, palm kernel, palm stearin, and cocoa butter. And you can see that by and large, our data agrees pretty well with what's been published. Next one. In the course of this work, we noticed that there were outliers between the various methods. HF, our data was only 3. There were 10 outliers from DSC, 3 from ECN, and 2 from GC and Westorp. Melting point data, there was only 1 outlier from our study. Here I've kind of summarized Gibbs free energy. Pure triglycerides are 0. Commercial fats and oils are 0. Hydrogenated oils are 0. And interesterified oils are 0. And of course, that just tells us that the melting properties of triglycerides are not spontaneous. This is the Gibbs free energy from the commercial fats and oils. Now, Westorp's classic model is based upon the Margulies activity model, and these are expressed as power series of the various mole fractions of the mixtures, and it measures the deviation from ideal solubility or Raoult's law. I mentioned that during the period where trans fat labeling became law, a lot of companies went to palm and palm kernel oil, and here's a puff pastry material made from hydrogenated soybean oil. This is one that was made with a palm-based shortening. Here's one with a palm-based puff pastry. It's got nice height and grain. Here's one of their competitors, and you can see that it's not a very good result. This is an old slide, but I've plotted life expectancy in years versus per capita consumption of fats and oils. Here you can see that from 1900 to 2000, life expectancy is increased from about 48 to 80. during this period, animal fats were primarily the food fats. Here, hydrogenated fats started to appear in quantity, and to me, it's questionable whether hydrogenated fats have caused coronary heart disease to any great extent. Next slide. So in summary, trait-modified oils are becoming important players in the food industry, particularly concerning health and nutrition. Oils with low saturates, high in omega-3 acids are in the pipeline and will soon be commercialized by the agribusiness sector. Processors continue to innovate to bring healthy oils and products to their customers with new technologies. Health and nutrition benefits outweigh economics in food applications. Products with known health claims will sell despite the increased cost to produce them. Biotechnology is becoming a very versatile tool for redesigning oils. But the goal is to balance functionality, oxidative stability, and nutrition. I would be remiss if I didn't show a slide showing the various mentors, colleagues, and heroes that have impacted my life, both at the Northern Lab and through the American Oil Chemist Society, and last but not least, my parents and my grandparents and my wife Marlene's parents, and my wife, who has stuck through me through thick and thin during my my ride. So I want to leave you with something that a life is past, but only what's done for Christ will last. That's a quotation from a famous missionary. So, in all things that you do it for Christ's glory and not the accolades of men. So thank you all again for coming, and it's been a wonderful opportunity. I'm very impressed with the Kansas City section. They did an amazing job, and I think they deserve a round of applause.